Unfortunately, our talk has absolutely nothing to do with the previous slide, at least not directly, although you can try and figure out what it actually does. We're going to look at how we can improve performance of or utilization of our available hardware. And here's a graph that I made of my CPUs. And this is a 4-core machine, but using hyper-threading. So you can see that I'll try how this works. At the top here, cores 0, 2, 4, and 6 are all almost 100% CPU, but not at the beginning. At the beginning, there's a bit of black in the picture. And we want to see how we can get rid of the black and have more green. So you end up with this type of picture. And of course, get lots of utilization of available hardware. Now, we're going to get there after a few steps. So the way that I do this talk is to have every separate step as a separate commit in our GitHub repository. So you can afterwards go through the GitHub repository and look at each step if you're interested to see. But I need your help because I often forget to commit whilst I'm doing my talk. So if you see me not committing a step, please stop me and say, commit, right? Any project managers here who can fulfill that role? All right. So we're going to look at a little example that you probably know called Fibonacci. And the reason we're looking at it is because it's computationally quite expensive to do. And the mathematical formula is dead easy. It's f of 0 is 0, f of 1 is 1, and then f of n is the previous two numbers added together. So basically at every point, the next number is almost twice as big as the previous number. And you can see the effect there in that picture where we're going round and round and getting bigger and bigger as we go through. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 5 plus 3 is 8, and it keeps on going bigger and bigger. Now, the numbers do get very big. Anybody from Australia here? Any Australians? Got to be an Australian here. No Australians? Well, Australia had this problem with rabbits, where they didn't have very many natural predators, and the rabbits just went crazy, reproducing like rabbits. And they eventually had, billions of rabbits running around Australia until they managed to solve that problem. So the numbers get very big very quickly. Now, if you write a naive implementation like this, where you say long of f, int of n minus, if n is less or equal to 1, return n, otherwise return f of n minus 1, plus f of n minus 2, if you have a direct conversion from maths into Java like that, you actually end up working out the previous numbers over and over again, and the computational time complexity of this function is in itself a Fibonacci series. Therefore, it's going to get very slow very quickly. It's almost exponential time. So you end up taking an incredibly amount of time to work out a relatively small value of Fibonacci. So one way we could solve this is to only work out each number once, to basically go from 0 up to n, so not have recursion, but use iteration and only go and work out everything a single time. And this ends up with linear time complexity as opposed to exponential time complexity. And the problem, of course, is that long doesn't get us very far before it overflows. I told you the numbers get very big. And right about Fibonacci 93, the 64-bit long overflows, and you end up with negative values. So the answer is wrong, but you get it very quickly. So it also doesn't really help us. So the solution would be to take big integer, which doesn't overflow. It allows you to have a number as large as you want. And this is great, and it works, except that the add function is has linear computational time complexity. So it's order n for the add. Now, the algorithm is n, and the add is n, and it's n times n, so it's n squared. So it's basically your bubble sort all over again, time complexity. And with this, you can work out relatively small numbers of n. 100,000 you'll be able to work out within a reasonable amount of time. But the moment you get into millions and hundreds of millions, it will just take too long to work out. So the next thing is to change the algorithm. And the algorithm that we start with, or the algorithm we're going to start with first, is Dijkstra's sum of squares. This is a much better algorithm because at every point we're dividing n by 2. So the actual algorithm from 0 up to n is logarithmic time complexity. So this already is a big bonus forward to improve that. But you do see that inside there we've got several multiplications. We've got, first of all, f of n minus 1 squared plus f of n squared. And down here we've got, again, f of n plus f of n times f of n. And this means we've got multiplications happening as well. And multiplications are quite expensive, very expensive. There used to be order n squared in big integer. In Java 8, they improved that to now be either ordered n to the power of 1.585 if they use a Kabutz complexity, or n to the power of 1.465 if it's Cook complexity. Now, I'm sure you know how these complexities work. The idea is that normally there's a constant setup cost, and once you overcome that constant setup cost, it starts becoming worth it to take, for example, Cook over Kabutz, or Kabutz over the big integer. So depending on what your computational, on what the size of your number is, it would, if it's a small number, it's not worth it to go for Kabutz or Cook because the cost of setting it up is so much that it's faster to just do the order n squared complexity. So you always have a constant setup cost, and once the problem is big enough, it's worth it to go for the more expensive setup cost because you end up, getting a better deal in the end. And so they've got certain threshold values beyond which they use Kabutz, and then if it's even bigger, they're going to use Cook. Now, I studied this a while ago, and I sort of figured out, understood how Kabutz works mathematically, but I've never understood how Cook works. Right? It's a far more complicated algorithm, and Kabutz splits the numbers into 2 sections, whereas this splits it into 5 sections, 5 segments, and then multiplies them individually. So I've never tried to understand Cook, and I will never try to understand Cook, but we will parallelize this in a later step. So without understanding how the algorithm works, we're going to still parallelize it. And that's the whole point of this discussion, or this talk, is to see how can we take existing code and make it parallel. So at the moment, we've got this better complexity in Java 8, but the multiplier is still just a single threaded multiplier. And we will change that in big integer a bit later. So the first step we're going to do is to take our existing algorithm, which is the very basic mathematical, straight from maths to Java, and we're going to change it to Dijkstra's sum of squares, which has a better computational time complexity. So let's try that first. And so let's get rid of this one. Don't need this anymore. Now, I did an estimate of this algorithm as it is at the moment with the computational, with exponential time. And I did an estimate based on, the time it takes to work out Fibonacci 30, 40, 50, etc. And I estimate that to work out Fibonacci 1000 with this algorithm will take 10 to the power of 200 years to calculate, right, with this algorithm as it stands now. We're going to change it to go to calculate it under 10 milliseconds. So that's our first job. And simply by changing the algorithm to better algorithm. So we're going to say this. We're going to say, let's change this to an if. And let's do this like so. So first of all, we're going to say half equals n plus 1 divided by 2. That's half of, it's for both cases if it's odd or even. And then if n is an odd number, then we have this algorithm over here, this algorithm over here. And if it's an even number, then we have the other one. So we're going to say, we also need to do this, we need to say big integer f naught equals f of half minus 1, and f of 1 will just be f of half. And then if n is percentage 2, if it's an odd number, we say return f0 dot multiply with f0, and add to that f1 dot multiply with f1, like so. Otherwise, if it's even, then we say return f0 multiply by 2. How do you do that? Any ideas? Shift left, very good. So we shift left by 1, that's the same as multiply by 2, dot add f1 and multiply with f1. Fantastic. Now, when we run the Fibonacci test, make sure it's running correctly. Yep. When we run it, we'll get some times. Now, as I mentioned, Fibonacci 1000 would have taken before 10 to the 200 years to complete, estimated. Of course, I didn't try it out. And now it takes 4 milliseconds. So that's really the big win. And that's sort of, if you can take one thing from this talk, is forget about parallelization, forget about anything else, just fix the algorithm first, and then you can talk about any other sort of optimization. Because you're never going to beat that type of improvement in performance. And it's busy running now on the 100 million, and it should be running, I would imagine, with 100% CPU, because everything is single threaded at the moment. So you can see Java, okay, that's finished now, but Java is running at 100% CPU. Let's go back to our output. And for the Fibonacci 100 million, which is one we care about, we took 43.6 seconds. All right, so that's the first one. Step 1, right? And we'll quickly do a git commit. So we can see this later on. So this is 43 seconds, and it's fairly good, but at the moment we're just using one core to do the calculation. And it would be nice if we could actually now if we were able to do this with multiple cores. Now, one of the features we can use in Java, since Java 7 actually, is this thing called ForkJoin. What ForkJoin does is it says, let's take the task, and if we've got 2 parts or multiple parts to the task, let's do one possibly in another thread by forking it. So you take this f of half minus 1. It was the first f we worked out, and we actually surround it with an element in a class called recursive task, and that is just going to call return of f half minus 1. So, and then we fork that, which might start it in a separate thread using the common fork join pool actually, and then we work out f of half, and afterwards we join back with f0. Now, we start doing this with the highest level number, so for example 100 million. And of course what can happen is that we would fork again within each of the subtasks. So you can end up within a very short while having lots and lots of possible tasks that could be running in parallel. Right, so by doing this, we should have thousands, hundreds of thousands of separate tasks running, or possibly running, within the common fork join pool. So we should be able to parallelize quite effectively using this approach. So let's do this as well as a second demo, and that is we're going to parallelize it. So we're going to take this calculation and we're going to spawn it separately in a separate task, which might or might not run in a separate thread. That depends on the configuration of your system. So here we're going to say recursive task of big integer f0 task equals new recursive task, and the method is going to return whatever we want to work out for f0, like so. Then we say f0 task dot fork, And afterwards, after we work out the other half, we say f0 equals f0 task dot join. So the principle that I use here is to always have only one fork outstanding. So if I fork, then I wouldn't do fork and then join. It can cause issues. You can have an explosion of threads and too many threads actually being constructed like that. So this tends to work the best. So we fork, work out the second half, and then join together. A variation that you could use here, which actually wouldn't be a bad idea, is to only fork if the number is bigger than a certain size. So we only fork up to a certain level. Now, if you take, for example, a parallel stream in Java 8, a parallel stream will fork up until 4 times the number of hardware threads by default on your system. So if you've got, for example, a big array or big collection, you're trying to somehow do some manipulation, map reduce or whatever in parallel, and you've got a 32 core machine, it's going to do 32 times 4 different tasks. It won't split it more than that, because you don't want to have it split into 2 small pieces, because then the cost of managing those pieces is actually more than the benefit you get from doing this splitting. Okay, but this should give us some performance improvement. Now let's run this code again and see how it performs. Of course, 1,000 won't make a big difference at all. The 100 million, should now be faster. And it should use the available hardware, because we are splitting into hundreds of thousands of individual tasks. They should be now running across all the cores and keeping everybody busy. And we would expect to see a 4 times speed up, because I've got 4 cores in this machine. And if you look at it now, look at the value, it's actually finishing just about twice as fast, as opposed to 4 times as fast. Right? So we didn't get the performance improvement we wanted. And what's interesting is, I'm going to run this again. Let me just comment out the tests we don't really care about, which is the smaller tests. We only care about 100 million. I'm going to run this again. And this time we're going to have top running at the same time. And you'll see something, I think, quite interesting. Look at Java performance. 600%, 600%, 400%, 300%, 200%. Right? It's getting less and less utilization. And then the last one, which actually runs for the longest time, is at 100% CPU. So we're starting running very nicely in parallel. But towards the end, we get down to 200% and then 100%. Any ideas what's happening here? Yes, sir?
As the joins are coming together, then one less CPU to use each one.
Right. So almost right. Very, very close. Okay. So I think what you meant to say is, as you're merging the numbers at the end, you're working out. So we start with small numbers, and we are multiplying them together. But the last numbers that we are adding together, they actually start to dominate this whole thing. Right? So the final multiplication is what's taking the longest time. And remember that multiply is still happening single-threadedly. So because the multiplier is still single-threaded, we actually not managed to do 400% CPU all the way through until the end. So thanks, very good answer. Let me commit this quickly, and we'll commit, say, step 2. So, the next step is to hack big integer. Right? Now, big integer at the moment is single-threaded. If you call multiply, it just uses one thread to do the multiplication, and this is what's hurting us, because we do actually want to do all the big multiplications with multiple threads, or at least have the possibility of doing this. So we're going to change this to we're going to change multiply to cook and square to cook. Both of these algorithms are going to be changed to allow for this parallelism. And then what we do is we compile the big integer, just like a normal Java C compile. And then when we start our program, we're going to point it to the hacked big integer with -x boot class path. Now, in Java 9, they tried to make this a bit more difficult for us. So in Java 9, you first have to create a patch, and then you have to compile against the patch, and you have to basically link in the patch. So there are 3 steps in Java 9. You can do it. You can do the same thing in Java 9, but it's a lot more involved. So we'll just do it for Java 8 to save ourselves some time. The basic principle is the same. So let's try that out. Let's go and come on, go away. Okay. This is not. Make sure stay connected to the power. Otherwise, we're going to have maybe different results. Okay, so Fibonacci. Now, what we do is we go to big integer, and I'll teach you a way in which you can get a better performance review next time you have a performance review. So often they look at how many lines of code did you write. Okay, so this is how you do it. Control A, Control C, right? And then you go and Control V, and you've just written like 2,000 lines of code. Yay, big bonus. Fantastic. And what we're going to do is we want to use this hacked integer. So we're going to say static using hacked big integer. I want to make sure that we're using it, right? So when I run my code at the moment, it won't use it. You don't see the output. But if I start my program again, and one of the parameters is a boot class path, I say /p, which means prepend. So I'm prepending whatever my path is to the Java math big integer. Then it's going to use this hacked big integer rather than the normal big integer. So let's run this again with the hacked big integer. And now I can see at the top there using hacked big integer. Okay, so bingo. Now let's change it. All right, so we're going to go to square tomb cook. And if you look in here, as I said, I don't understand how this algorithm works. And I don't want to know how it works. I just want to parallelize it. So without understanding it, I can parallelize it. Now, there's a reason why this works. And the reason why it works is that this class was written without state, right? Or that they try to not have, it tries to be an immutable object. It's not exactly immutable, but you can treat it like immutable. So if they had intermediate state, this wouldn't work. So we want to be very careful of classes that shared state, because then you all of a sudden have parallelism and multi-threading accessing shared state, and then things go horribly wrong. But this class, it will work. Now, let's go and take this over here. I'm going to fork this one, and then I'm going to do the second square. The third square I'm going to fork, and then I'm going to join in at the end with the ones which are forked. And I always want to join before fork again. It's sort of my way of doing it, which seems to work very well. So let's make this time an inner class, private static class square task extends recursive task of big integer. And then we're going to say in the compute, return a.square, where a is going to be a field, big integer, final of course, and we put in a constructor parameter for a, like so. So there's my square task with a big integer a, and by the way, that name might seem like not a good field name, but that's actually what they call it inside big integer as well. So we can actually we can use that as well. And then we use this inside here where we've got the square. We're now going to say square task v naught task equals new square task of a naught, which is what we are going to be squaring inside here. We fork it, and then after we do before we do the next square, we join. So we can say v naught equals v naught task dot join. And we do the same thing for v1. We say square task v1 equals task equals new square task of da1, and then v1 task.fork, and once we've done the next two squares actually here, we're going to say v1 equals v1 task.join. So we're forking and then joining back together again. And of course, each of the forks potentially could create another fork, because if the number is still too big, it's going to fork again and fork again. So you end up with having quite a few tasks as a result. We're going to do the same thing for the multiply Toomcook. Toomcook 3. There. We're also going to have a multiply task. So it's private static final class multiply task extends recursive task of big integer. Private final big integer a comma b, set that in the constructor, and then down here we're going to have a compute function which simply says return a dot multiply b. So that's the multiply task. So it's basically the same as before, multiplication, but put into separate tasks, which now will automatically be run inside the common fork join pool. The moment you fork from a thread which is not in the common pool, or it's not inside a fork join pool, it uses the common pool to do the calculation. So this makes it very easy to patch this into existing code. So it's going to be the multiply task now, multiply task, v naught task equals new multiply task, which is a naught comma b naught. That's this over here. And we're going to say v naught task dot fork. And before we do after we do the next multiply, before we do the third multiply, we're going to join it. We're going to say v naught equals v naught task dot join. So we fork it, we join before we do the next fork. And here we do the next fork with v1. So we're going to say multiply task v1 task equals new, which is da1 comma db1, v1 task dot fork. And before we do after the last multiply, we're going to say v1 equals v1 task dot join. Okay, so now hopefully we'll be able to keep our utilization fairly high for all the cores. We'll see now. We're going to run this against top and see what the percentage of time in CPU is. Okay, so there's Java. And you're running at. Okay, so we're running at a much better utilization, and keeping ourselves busy until the end. So we've now achieved one thing we tried to do, which was to keep all the cores busy, right? So that's great, and we've got a nice speed up here. I think it looked like it was faster, down to 15 seconds. All right, it's factor 3 speed up. I've got 4 cores, so that's it's okay. It's not fantastic, but it's okay. So this is now our step 3. And quick. Step 3. Now, what else can we do to speed this up? Well, what's interesting is that if you look at the numbers that need to be calculated for Fibonacci 1 million, for example, you start with the first at the top. Where was it? This one. At the top, you start with 1 million, and 1 million is split into 49999 and 500,000. And then 4999 is split into 499999 and 250,000. But so is 500,000 also split into 249999 and 250,000. So at every level, there actually are quite a few duplicates of the numbers that are being generated here. Right, so that's the first thing that you need to be aware of. Okay, and at the end, like level 14, for example, you've got 7,900 times Fibonacci 60 being calculated. So as you go down the levels, you end up having more and more duplicates of the same thing being calculated. So, so what we're going to try next is a something that I actually wanted to do. Let me just quickly show you something. Is this unskip and unskip. So one of the things that I'm offering you guys just today, until the end of my talk, is to subscribe to my newsletter and get a free license for a mini course on Java 9 using Java 9. So a bunch of Java 9 stuff. If you subscribe to this, Java JAX tinyurl.com JAX London 17, you'll get, as I said, a free license to the mini course on Java 9, which looks at how to do non-blocking network communication. It's quite fun. I did that course last week, so it's hot off the press. And I'll also subscribe to my newsletter as well. So I'll put this up again at the end of the talk. But at the end of the talk, this is going off. It's not going to won't work anymore. It expires. So what I wanted to say is our fourth step is to try and avoid doing the same thing over and over again. And we do this with a cache. Now we've got to be careful with caches because we don't want to have a static cache, because a static cache, a static field, tends to cause memory leaks. It very frequently causes memory leaks. And we don't want to do that. We want to have a cache which is only temporary. Even that can cause problems if it gets too large. So we're going to, hopefully it won't be too big, but hopefully this will improve our performance. We're at 15 seconds at the moment, and we want to take advantage of the fact that we've got lots of duplicates over here, that a lot of the numbers are actually the same that we're trying to calculate. So we want to cache them inside a map. So let's try and do that as well. Right, so in here, I'm going to have two functions f. The one is the old one, and it's going to start off by creating a map. So we're going to say private map from integer to big integer, cache. Now it needs to be a thread safe map, so we're going to use a concurrent hash map for that. And then we're going to say cache.put 0, and 1, 1. And then we're going to say return f, the cache. Sorry, fn, the cache, like so. And this is going to be the second parameter of the function, this one here. And so whenever we call it down here, we need to now call f with the cache and f with the cache. And then what we want to do, we don't need this, this must go to the top, sorry. This must be over here. The method should be private, of course, because we don't want it to be seen from anywhere else. And we don't need this if statement, because we've covered that by seeding the cache with 0 and 1. And then over here, we can do the following. We can say big integer result equals cache.get n. If results is null, then we work it out and we say result equals and result equals, and we say cache.put in comma the result. So we put it in if we've calculated it. And then we say return the result. So this is our new code over here. So we get the cache, get the value from the cache. If the result is null, which means we haven't worked it out before, then we calculate it, we put it into the cache, and now we should greatly improve our performance, because we're not going to have all these cores working on the same work, trying to calculate the same numbers. Let's try it out. The CPU should still be 100%, 600% or whatever it is, a much bigger number than before. And we have actually improved the performance quite a lot. So we're looking at 9 point something, almost 10 seconds, just under 10 seconds. So that's quite a good improvement by caching the values. It's not as much of an improvement as we were hoping, but it is an improvement for sure. Right. Is there any better way that we could do this this cache? If it's not there, then put it in, then calculate it and put it in there. Any suggestions? Yes, sir.
Computed absent?
That's what I tried. And when I tried that, let me show you what happens when you try that. So I think that they might even suggest it. No, they don't. I don't have this refactoring set up. But so the idea is the following, that this calculation goes into Lambda to calculate it. So you're going to do this. You're going to say, let me just make a copy and paste of this. So we'll, okay. And then what you do is you say, result. You can simply say return cache.compute if absent in comma, and I pass in a lambda where you pass it in a key, which we don't actually need to use, and it then does this calculation and does the cache put for us. So we just say return and return, and that's all we do. So this is the compute if absent. This is Java 8 syntax for doing this, and this looks much better than what we did, because before we sort of manually tried to see if it's null, then calculate it and put it in. This is much better. We can just say, well, if it's not there, calculate it for me and put it in. Right? There's one little catch: it doesn't work. Right? And the reason why it doesn't work is because it's not supported. Because what we're doing is we are modifying the structure of the map inside the compute function, which you're not allowed to do. This is a sort of feature of maps, that compute if absent is not allowed to change the structure. Now, what's funny is if I change this to a map instead of to a hash map instead of concurrent hash map, it probably will work. It probably will work, but of course it's not correct because it's not thread safe, right? But it's working because I don't have that many threads which are hammering the map at the same time. So probably it will work. Probably it'll run through. So it works without failure, but it's also incorrect. And if you run this in Java 9, it's going to fail. Java 9 is going to say recursive update, I think they call it. They give you a concurrent modification exception if you do this with normal hash map. And concurrent hash map, they give you, I think, an illegal state exception if you do it. So even though this seems to be like the perfect use case for the compute if absent, it actually is not allowed to do. You're not allowed to do this. You're not allowed to change the structure of the map in the compute function. It is documented some way, but it's quite hard to find that documentation. What's also interesting about this is that usually subclasses are not allowed to throw exceptions except those which are declared in the superclasses. The principle of least surprises. We don't want to have a surprise when you call the subclass and then boom, something else comes back. You were expecting this and you get a different exception. And they are very consistent in the JDK except for this method. With this method, they break that rule. With this method, they declare in inside the superclass that you have a certain type of exception, and the subclass are throwing different exceptions in concurrent hash map and in hash map. So that's quite interesting, a deviation from the way they normally do things. All right, the question is, did I commit this? Anybody know? I don't think so.
Some kind of double check locking? Look it up in the cache without obtaining a lock, and it's not there.
Right, okay. So you mean for the compute or what?
Yeah.
We'll solve it in a different way, because that's what we're essentially doing here. We're actually doing that whole thing. We're saying, get the value, just get it, and if it's not there, then compute it and put it in. What the compute if absent tries to do is it tries to do that in a... Actually, what I need to also do, sorry, before I need to also add big integer. Git add attack source. Okay. Okay, so what I was saying is that, what was I saying before I got distracted? Anybody remember? Double locking, right. So what computer absent tries to do, especially with the concurrent hash map, it tries to ensure that only one thread actually calls that function. So you don't have multiple threads calling it. This also means that there's locking going on the computer absent function. Now, I believe they're trying to solve this for Java 9 to reduce the contention, because at the moment, if you've got lots of threads which are calling computer absent, and there are relatively few unique keys, you have crazy amount of contention on the concurrent hash map. It's very bad, you know. So we want to be very careful of using computer absent. I normally recommend you don't use it at all. Or if you're going to use it, you want to first want to check, is the element there? And if it's not there, then you use computer absent. So you first call get and then computer absent, because otherwise you can end up with very bad contention on the map. All right, this was step 4. Excellent. So what we're going to do next is we're going to use something called put if absent, as opposed to just get. And when we say put if absent, what we're going to do is we're going to put in a special placeholder object. And what this means is, if you call put if absent and you get back null, it means that you were the first thread, the first user, to try and calculate this number. So you're the first. Because you're the first, you start calculating. But if you get back that special placeholder object, it means that somebody else beat you to it, and you now wait until they're done to wait for their answer. So that's how we're going to do it. So if we get back null, it means we were first, we start work. Otherwise, if we get back the placeholder, then we wait until the first one's finished. Otherwise, it's a valid number, you just simply return it. So there are 3 different possibilities here. So let's code this as well. And the first thing is we're going to say, instead of get, we say put if absent in comma a special value, which is going to be a constant field equals big integer dot value of minus 1,000, for example. So some number, I'll make it just private final, not static. And you could potentially have a different big integer per slot if you wanted to. But we're going to just have one to make this simple. And so if the result is null, we start calculating. That basically remains almost the same. Else, if the result is our special reserved object, it means that somebody else beat us to it and is busy calculating. So he's not finished yet, he's still busy calculating. We're going to say try synchronized. We're going to synchronize on reserved, and we're going to say while results equals cache.get n is not or is equal to reserved. As long as it is still equal to reserved, we're going to wait. So we're going to keep on waiting until eventually we get the value. Now, if we get interrupted, we're going to say throw a new cancellation exception. Interrupted. We're not going to just ignore it. We're going to actually rethrow that, like so. So this is going to wait until it's no longer equal to reserved. Whilst it's equal to reserved, we wait. And then it's where the put is, we're going to wrap this with a synchronized. And we're going to say synchronized on reserved. We call cache.put. Afterwards, we're going to say reserved.notify anybody who might be waiting for this value. So this is like a post box, a messaging scheme. Anybody who wants to work it out and you see someone else is working, simply says, okay, I'm going to wait for them to finish. And then the thread which is calling the put notifies anybody who might be waiting that I'm done now. All right, let's run this and see if this improves things a bit. Right, so we actually got part of it better. We went down to like 7.2 seconds. And that's great. That's on a step 5, 7.2 seconds. That's a great improvement from 9.9 seconds. We're doing less duplicate work. And if you run this code together with top, let me just get top up and running. Okay, and let's run it again. And you see that top is fairly busy. Okay, now with this number 100 million, the number is fairly small. So at the beginning of the number, well, fairly small in comparison to other numbers I've worked out, at the beginning of the number, there is a section where quite a few of the threads are actually waiting on the waiting state. Now it's slightly obscured because I've got hyper-threading on. Because I've got hyper-threading on my Mac, and I don't know how to turn it off, because I've got it on, it's got two hardware threads and two threads per core, right? And actually there are quite a few threads waiting, but because I've got 8 threads which are trying to run on 4 cores, things sort of work, right? If I had a machine where I really only had 4 hardware threads on the 4 cores instead of 8, so hyper-threading turned off, I would actually find that my utilization is much worse because I don't have enough threads to keep the cores busy. You can see it if you make a thread dump. So, for example, if I run this and I say thread dump at the beginning, and I'll do another thread dump a bit later, and you'll see what the threads are doing. Oh, no, I missed it there. Let's do it again. So, thread dump, and then after a few seconds, another thread dump. Now, if you look at what the threads are doing, I'm going to find them here. You can see here, for example, here's a thread that's doing some work, runnable, which is good. Runnable, that's 2. But this one's waiting, runnable. So I've got four threads which are runnable and 4 threads which are waiting, right? So half of the threads are actually in the waiting state. And as I said, because I've got twice as many threads as I've got cores, it sort of works. But if I've got a one-to-one between number of cores and number of hardware threads or number of threads, it's going to be not a very good utilization at all. So how do we fix that? This is now the last point. Before I do that, a quick commit. Step 5. And what we do is we can tell the ForkJoin pool when we're going to be waiting, when we're going to suspend a thread for a while. And we can say, please, you manage that. You see the ForkJoin pool, when you construct it, you normally specify the desired parallelism rather than the number of maximum threads. In Java 9, you can specify the number of maximum threads, but before Java 9, you couldn't. So what you can do is you can say to the thread pool, to the ForkJoin pool, we're going to be blocking now, and please manage this so that we still have the same number of threads for doing the work, to keep the parallelism high. And there are two classes that do this at the moment out of the box. The one is phaser, Java 7, which nobody knows, and the other one is completable future from Java 8. So these 2 classes do this out of the box, that if they're going to be blocking, they tell the ForkJoin pool, I'm going to be blocking. Please create more threads to keep the parallelism the same. So that's what this does. Now, let me show you how to do it. This part's actually the easiest of the entire demo. We basically take this code over here and we wrap it inside a class. And we separate it into 2 parts. This over here is the one part, which is actually your condition predicate. And then this is the way that you're going to be waiting. So it's 2 parts. And private class reserved blocker, we'll call it, implements ManagedBlocker from ForkJoin pool. It's got 2 methods, block and is releasable. I'll swap them around. And basically, block is going to be looking like this, except that that's from the before. This is going to be moved up here. And we're going to do one little change here. Private final int n, private final I need to get that map. I don't want to type that in again. It's too much work. The cache, and then private big integer, the results. So this is the results, and I need the constructor for the in and the cache. And then what I want to do is releasable says the result equals cache.get is not equal to reserved. Right? That is releasable. Now, if it's not equal to reserved, it means that there's no need for going and locking it. It's basically, this is your condition predicate. Now, in this case, when I call cache.get, it doesn't modify the cache. If I was going to modify the cache, like if I said cache.remove end, then I should actually first check that that result isn't already not reserved before I start. So I have to check if result is not equal to null and it's not equal to reserved, then do this. Or if it's equal to reserved, or if it's equal to reserved, then do this. So, but because get doesn't change anything, it's a non-modifying method, we can do it like this. This will work. So over here, I would now say, while not is releasable, reserve.wait. So whilst I'm not releasable, wait. Okay, so this is the same code as before, but just inside implementing interface that we can use for managing this blocking. Okay, and then we construct an instance of that over here inside our, where we had the synchronized before. We're going to say now reserved blocker equals new reserved blocker with n and cache. And then we say ForkJoin pool.ManagedBlock of the blocker. And then result equals blocker.result. This is important, otherwise we're going to get the wrong result at the end. It's going to be minus 1,000 every time. Now, it's not going to make a huge difference on this machine because, as I said, I've got hyper-threading on, and that actually obscures things a little bit. But let's run it, and made an error. Let's return statement. That must be return true. And yeah, sometimes I get unlucky. Sometimes it's actually slower after my change. But such is life. It's almost the same. You can't see it so well, but what I'll do is I'll actually make a thread number, and you'll see that we've got additional threads that are being constructed to take up the slack. So for once, the demo does not work in the way I want it to work, which is a pity. But you'll see now that I've got now common worker 18. So it actually created up to 18 threads. Not at the same time, but just to, as soon as one waits, it creates another one. And once the waiting one is finished, it drops that and continues with the new one that was waiting, that was taken over from there. So you have more threads which are actually in the runnable state than you had before. You should also have a total, possibly more threads at the same time. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So in total, we've got 10 threads, including the main thread, which are working on this problem, rather than just 8 threads with some of them blocked and waiting. Thank you very much. Right, so this is was one more slide, which is basically an exercise for you to do, because you can do a similar thing using the principles I've talked about, using computable future, right? And you'd also use a cache. You'd use this diagonal sum of squares algorithm. So a lot of the elements that I've shown you'd have to reuse. And what you can do is try this out with computable future. The two methods that you can use is then accept both async and complete. And with that, you can actually parallelize something quite similar. And let me know if you can figure it out. You can also try what happens if you disable the common fork join pool. You see, in a server environment, often you don't want to have parallel streams, for example. So you can turn them off. You just say minus d Java to concurrent fork join pool, common parallelism equals 0, and then it's turned off. There's no more common parallelism. There's no more common pool. It doesn't have any threads. But things go a bit funny with computable future when you do that. So you can try that out. So this one newsletter that I write, Java Specialist newsletter, and this was this offer that I gave you guys. If you're interested, please sign up there. Any questions? Yes, sir.
Do you think you get any speed up if for smaller inputs you didn't bother waiting for the cache to be calculated, but you just calculated it then anyway?
Sorry, if you calculated that for small inputs?
Yeah, so instead of waiting for the reserve to complete, you just went ahead and calculated it anyway and ignored the cache without.
Oh, right. Okay, so this is a really good idea, actually. So the idea is that there's a cost. Let me summarize what I think you're saying. What he's saying is that there's a cost in suspending the thread and reactivating it afterwards, waking it up afterwards. You're forcing a context switch. You're doing a voluntary context switch, which is very expensive. So to avoid that cost, if the number is small, it makes more sense to just say, you know what, we don't really care. We're just going to just calculate it. We're always going to calculate it if it's below a certain threshold. I didn't put thresholds into this code, but you probably should, both for that and for the splitting, because for the same reason that you don't want to split small numbers, because each of the numbers is so quick to calculate, it's not worth it. So yes, that's a very good idea, to actually only suspend and wait if it's a small number, otherwise just work it out. In fact, then you can always work it out. You don't have to worry about anything else. Just work it out and put it in, and you're going to probably save time. It's a very good idea. Yes, sir?
With new CPUs having 18 cores,
Yes?
it becomes too hard to try and handcraft parallelism. And
Yes.
is that why you see more stuff to do with actors and flows and status things?
Yeah, so I'll just repeat the question because for the recording and for everybody else. The question is with new machines having 18 cores, 36 cores, lots and lots of cores, to manage an algorithm like this becomes tricky. The easiest way to parallelize is to have lots of tasks which have the same size, approximately the same size, rather than what we're doing here is a little bit tricky because the tasks all have a different size, or most of them have a different size. And to parallelize it is actually not so easy. So what we do with most systems is we get the speed up by having lots of tasks, which all are relatively small but are running in parallel. That's where the actors come from and things like that. So here we try to solve one problem by breaking it up smaller and smaller, as opposed to solving lots of problems at the same time. Yes, sir?
Just wanted to know, this technique, can we do, say, find out something like a given number of permutations?
Given number of permutations.
This technique can be used for that.
Right, so you can use this whenever you've got a big problem you're trying to solve by the number crunching. You can break it up into divided by half, and do it separately. So it's the fundamentals of parallel streams. They use ForkJoin underneath the covers. So whenever you've got a problem that you want to break up, so the permutations you'd have to, if you have lots of permutations of some different values, you could do it with ForkJoin. Sure. At each permutation you could have a different fork and then go down that path. Where it gets difficult with that is, let's say that you're trying to discover one particular solution. Right? So you're looking for one that'll work. So you're throwing it at your 18 cores and you're saying, show me the first one that's actually going to work. So it goes into all the different cores and lots of different threads, but it's actually quite difficult to cancel a ForkJoin task or the ForkJoin system. It's very hard to cancel a parallel stream. Interrupts don't work with ForkJoin. So you can't interrupt the thread. It won't have any effect. If you say cancel with true, which normally says interrupt the thread, it doesn't actually interrupt the thread. And so the way to do that is to have a shared variable, like a shared volatile variable that says, found solution. So you'd have all the different tasks looking for the solution. If one of them finds it, it just marks that shared volatile field as true, that we found the solution, and then everybody stops looking. So you have to have some sort of poison pill for them all to stop. Otherwise, there's no way to cancel. They'll all keep on looking. Great question, thanks. Any other questions? Yes, sir. Yes, I will actually. It's under. It's on Kabutz, GitHub Kabutz / JAX London, something JAX London. Yes, sir.
Do you use this level of optimization for?
You do, yes. You do. I mean, this is used for parallel streams. It's used for completable future. Yes, sir.
Are any of the other non-Java JVM languages better for this stuff?
I don't know. Are other languages better for this? I didn't find this to be too difficult, to be honest, to do the ForkJoin, to hack it in. It used to be more difficult before Java 8 came along. Because before Java 8, you didn't have this common ForkJoin pool that you could just use. You had to create a special ForkJoin pool to use for this. And then configuring it and knowing the right sizes. And the problem with having thread pools is that if lots of different parts of your code construct thread pools, you get an explosion of threads in your system, far more than you really want to have. Having a common ForkJoin pool, I think, is the right idea, to have one place that we use. Any other questions? And one more thing I need to do before we go is step 6, and git push. Right. So turbocharge ManagedBlocker JAX London 2017 on my GitHub repository. So thank you very much for listening to me, and enjoy the rest of the conference.